Hi, Jeremy. How's things?
I'm all right. How are you?
Tired. Been a long day.
I didn't sleep last night.
You didn't? I'm sorry to hear that.
I had some caffeine to do my homework.
You had caffeine so you could do your homework, or you had too much caffeine so you couldn't do your homework?
I had caffeine in order to do homework, and
Oh,
it kept me up all night.
Uh-oh. Well, the moral of that story is do it earlier.
Professor, I believe that there's something not right with the progress report because in one of my progress recently made it said that my online test number 8 is really low, while I'm not seeing my online test grade on the website yet.
Oh, I can show you your online test grade. I just never got around to it, so I can do that right now.
Since I got 4%.
Does it
Yeah.
say 4%?
Yeah,
Oh,
I did.
If everybody's saying a 4%, then that is a mistake.
I don't know how, but I do also get 4% as well. Like, what the hell is going on in here?
I think that is quite clearly a mistake, but let's put it so you can see it, right? That way you'll see what it is. But I'm going to go in and change that. I think I must have just copied and pasted the wrong cell location, and that made everybody get 4 because evidently there was 4 in that location. That's weird, but never mind.
So same one we just took.
Right, that's that fix. You should be able to see your grade while I go in and say what went wrong. What test number was that?
8.
8, the last one. Okay, so that one does exist. So, oh, it's 3% in this one. Okay, let's find out what went wrong. I should be able to do it through mail, and then I should be able to do preview. And it says week 8. Did I not put week 8 in, or did I copy week 8 wrong? Okay, let's find out which that is. I'll get my spreadsheet on. Week 8 homework. It looks normal. So where did that weird number come from? Week 8 homework, double check it. It's called week 8, yeah. Okay. I bet you I took week 8 attendance. That's what I bet you I did. Which makes sense because it would be 3 or 4 for most people. Okay, so that's an easy fix. Now I've figured out what I think I've done. And it's exactly what I thought I'd done. I took week 8 attendance and not week 8 online test. Okay, that should take a few seconds. Cancel.
I found 2 more, what I think 2 more errors in my progress
Don't do
report.
that. I'm fixing this one. I can only fix one a day. That's all you're getting. There. Okay, that's me got a grump over. What is it? What are the 2 mistakes I need to fix?
So the one is on the homework. It's
Okay,
on
which
section
tried-
11.11.
1111. So 1111 has got 1111 applications. It says it's correct. Let me check it by.
But if you remember, those were the you taught us how to do the air functions formulas one way.
They haven't been fixed. Is that what you're saying?
Yeah.
Okay, that's something I do need to do. I do remember that conversation. That'll take too long, so you just have to wait until Thursday, but I will get that done. What was the other mistake? Or is that it?
I can tell you afterwards.
Okay, that'll work too. It may be just one you specifically rather than everyone.
Oh, I was wondering, have the test 8 been graded?
Yes, they have.
Oh,
That's
okay.
the one we just did.
The one you just did.
All right.
Okay, it said I got 4%, so I didn't know if that was an error. or if maybe-
No, you came in late. That's been fixed. So I'm about to send the fixed version.
Okay, I mean, if I got 4%, that's okay. It just makes me feel better.
No,
Okay, thanks.
the chances are you got more than that. I would
Yeah.
think you would. Okay, there's version 2 coming.
Should I tell the class the jokes I sent you?
Well, if you want people to stop being your friend, I think that would work. No, I'll shoot in space. Don't exit. Okay. It's taking its time sending those out, I think. 502. No, I think they have sent them out. Okay, I'm good. Yes, go for it, Jeremy. Tell them your joke. And tell them the one about the cat.
So Rene Descartes went to a bar, had a couple drinks. The bartender asked if he'd like another one. He said, "I don't think so." And he disappeared.
I didn't get that one right at the start, guys. So if you didn't get it, you're in my camp.
Rene
Cam,
Descartes
did
was,
you get that one?
Nope.
Okay, Jeremy, explain it.
Rene Descartes was a philosopher who said, "I think, therefore I am."
I don't think so. So if he doesn't think, he doesn't exist, so he disappeared. Do you see the quality of the jokes that we're getting? There are about 0.1% of Americans would get that one, and I wasn't in that 0.1% group.
Because you're not American.
True. Okay, I think everyone is here. Well, good morning, everyone. Good evening. I don't know what it is. I'm so tired I'm ready to go to sleep, but I'm not allowed to because they pay me big bucks to do teaching. So let's do some teaching. Section 13.4 is one we're going to be dealing with today. It's to do with space curves, and in particular, how derivatives tell us a lot about the motion of the curve. So I want you to imagine that's your standard jet flying in 3D space. There's its space curve, also called its, vector functions, another name for that guy. And we would like to know, in particular, these three things. We'd like to know the velocity vector, because it will be a vector in 3D space. 2, the speed, which, by the way, is a single number. So that's going to be a scalar. That's going to be a vector. And right now, acceleration, which is also a vector. So if you choose that point there, then that vector there could well be the velocity vector. And this vector going, say, that way, could well be the acceleration vector. We tend to use V for velocity and A for acceleration. So you can imagine your velocity vector represents the vector as you shoot off to your death on the roller coaster, right? You could shoot off to your death at 10 mile an hour or 10,000 mile an hour. That number, 10 or 10,000, is what we mean by the speed. And so we can calculate all three of them relatively straightforward. So here is our generic space curve. I'm going to call it parametric, x of t, y of t, z of t. If you want to know its velocity vector, it's just the derivative. Nice. I mean, if you did Calc 1 and s of t was the position vector, wouldn't the derivative s dashed of t be the velocity function, right? In the 2D world. Well, analogy here. Now, if you want to get the speed at any given point 2, the speed is the magnitude of the velocity vector. So a really long velocity vector means that you're going like 100 mile an hour. A really skinny one means you're only going 10 mile an hour. And we know how to get that guy, and that is our speed. And then if you want to get, well, I don't think it's going to be a big jump here. How would you get the acceleration function?
Well, from the old calculus 1, I believe that should be the derivative of the velocity, right?
You're correct, it is. So it's the second derivative of the position or the derivative of the velocity. They're totally equivalent. Does that kind of continuation from 2D into 3D go relatively smoothly, right? Now, when you say speed, speed is a positive number, right? You're going 50 mile an hour up the way, you're going 50 mile an hour down the way, right? So it's a fixed positive number. Velocity is a vector, it has a direction associated to it. So does acceleration. It's just a little bit harder to get your head around what is an acceleration vector doing, because it's really telling you three things. It's telling you how the X, Y, and Z components are accelerating, and they could be accelerating stroke decelerating at totally different independent rates to each other, right? So it could be going up the way really fast, to the right really slow, you know, if you call to the right the y-axis, right? And if you go the other, the x-axis, it could be going constant, right? Not changing at all, right? So they work totally independent of each other, which you might think is unrealistic, but that's how things move. So we are going to jump, I hope, right in and just do some examples of exactly those kinds of questions. So you're going to be doing a lot of differentiation. So put that over there as a little reference. I'm just picking a random polynomial to start the day off. So suppose it was t cubed 2t minus 1, 3t squared minus t plus 1. If I wanted to find the velocity vector of that guy there, I would differentiate. So it'd be 3t squared, 2, and 6t take away 1. And if I wanted to get the acceleration vector, I would just differentiate that, and I would get 6t, 0, and a 6. And if I wanted to get the speed, it's going to be a bit uglier. I would take the magnitude of the velocity vector. And to get the magnitude, you take this guy and square it. You take this guy and square it. And you take this guy and square it. And if I had room, I would probably, well, I can still do it, but it's going to be really tight. That guy is going to be 9t to the 4 plus a 4 plus 36t squared, take away 12t plus 1. And wouldn't you just tidy it up a little bit, collect like terms, make it look pretty? There's a vague chance, a very, very vague chance, but sometimes it will happen. Couldn't the thing inside the square root be a perfect square? Just now and again. And you have to try it out. I know that one's got no chance in Hades, right? But, you know, if you think it's got a chance, you should at least try, see if you can do it. I'm trying to make this obvious because I think it is. Does this seem obvious? If I give you a space curve, first derivative is velocity, the magnitude of that is your speed, and the second derivative is your acceleration. So really, oh, and they chuck in a question where they ask you to draw it, but can't you just plug that guy into GeoBra and this guy into GeoBra and that guy and just see what curves you get out of it? So I'm not going to zoom in and out of GeoBra, hopefully, because I don't need to. Let's do a combination of all sorts of things. What do I mean by that? Well, how about e to t squared? How about sine squared t minus t? And how about the natural log of t plus 1? Right. I could put that into GeoBra and it would look, I have no idea what it looks like, but it'll be some spirally curve doing its thing. I want the velocity vector. So I find the derivative. And if you want to differentiate this, do you recognize a chain rule situation? E to the t squared. So the t squared is like your inside function. So you'll get e to the t squared times the derivative of t squared. If you want to do this guy, you probably should think of it as sine t squared. So you get 2 times the sine of t, the power of 1, times the derivative of that guy, and then a minus 1. And the derivative of a natural log is just 1 over t, and 1 doesn't get you anything. And then you have style points. Sometimes you have a lot of style points. Sometimes you have very little. What could 2 sine t cosine t be better written as?
Sine of 2t.
Okay. So this is going to be the sine of 2t, take away 1. And this guy is just 1 over t. Now, if I want to get the speed, it's going to be the magnitude of this vector. I'm just going to write down what the calculation is. I'm not going to do the whole thing because it would take too long and it's really ugly. That guy squared, that guy squared, plus that guy squared. The only thing I'm pretty sure about is there's not going to be an awful lot of style points in that question. Would you agree it's just some big, ugly, horrible square root, and you live with it? And last but not least, to get the acceleration vector, I can differentiate this guy. So I'll leave that one for a minute. This guy at the end is -1 over t squared. If you differentiate this middle guy, you'll get the cosine of 2t times the inside function, which is 2. And what technique will I use to differentiate 2t e to the t squared?
Radical.
Agreed. Make this f, make that bit g. So you'll get 2 times e to the t squared plus 2 times e to that times another 2t. So that will get you 4t squared e to the t squared, and you're finished. Now, in case you're thinking, because I'm pretty sure, although I can't remember that far back in my math life, that if the magnitude of the velocity vector is the speed, I wondered what the magnitude of the acceleration vector would be. And evidently it's not that important because they never bother to ask you to do it. My guess is there isn't a kind of measure of the total amount of acceleration that's happening, you know, because it's happening in 3 different directions, X, Y, and Z, essentially independent of each other. So I'm guessing that the magnitude of the acceleration vector might be a measure of total acceleration in some sense. But since we don't do it, I'm assuming that it's not that interesting or useful. It's not hard to do, right? Physically, we could ask you, but if it's not necessary, they just don't bother. Okay, this is an example of theirs. And we have e to the t, a bracket, cosine of t I. You know, I don't like this notation, but I'm doing it for a reason. Sine of t j plus 6t k. And I'm doing it to show you how you would approach that one. Wouldn't you separate it into 3 separate multiplications? So product rule, product rule, product rule. I'm going to tell you the answer to that. You can check it later. But the answer to that is e to the t, cosine t, take away sine t. The middle one is 2e to the t cosine t. So I would have thought there's another term. Oh, there is. It's e to the t. There's not a 2 there at all. Cosine t plus sine t. And the third one, because I don't have enough room to squeeze that guy in, this one here is e to the t and 6 plus 6t. Now, each one of those guys involves a fair amount of work to calculate, right? What I'm saying is, look, if I wanted to get this one, wouldn't I have to do my own product draw? If I wanted to get the middle one, a different product draw. If I wanted to get this one, yet another product draw. So the answers are quite messy. And that is essentially our velocity vector. And all I'm going to do now is get the speed. So the speed is the magnitude of that vector. So it's going to be that guy squared, which is e to the 2t cosine t take away sine t squared. Then it's this guy squared, and that's going to be e to the 2t cosine t plus sine t all squared. And then you got that guy, who's going to be e to the 2t 6 plus 6t all squared. Have you noticed that each one of these guys shares a common factor? So if you pull that out and take a square root around it, can I write this down in one line rather than writing down the 2 lines? Right, it's like the square root of that ends up being this guy, right? So the square root of e to the 2t ends up. Now you FOIL this out, you FOIL this out, and you FOIL this out, you're going to have a lot of stuff. You're going to have a cos squared t minus 2 sine t plus a cos plus a sine squared t. If you do this one, you're going to have a cos squared t plus 2 sine t cosine t plus a sine squared t. And that one up there, by the way, is a right mess. It's 2 sine t cosine t, and then you have a plus sine squared t. That's what you got. And this guy here, you get 36 72t plus 36 t squared. This is all style points, making it look pretty. Do you see that horrible mess? Doesn't it get killed off by that equally horrible mess? Can you see anything else in this list that might become something nicer?
The pair of cosine t, cosine squared plus sine squared.
Would get you 1. And since you've got another one, wouldn't that get you 2? And couldn't you add 2 to this guy? And I like the t squareds first. So 36 t squared plus 72t, and that gets an extra 2, so you get 38. Checking that guy out, and I pretty much know right now it is not a perfect square. But you could play about with it and see if you can get one, but I'm really sure it's not. If it was a perfect square, wouldn't it be 6t? But do you see how that number doesn't play well with being a square? But if that was 49 or 25, I'd be much more likely to get something that works. Have we got any questions about velocity, speed, and acceleration? You feel comfortable about the process, even although it's going to take you a while, especially with the ugly ones? Are we good? Let's turn this question on its head then. Suppose I tell you the acceleration vector, and it's 3t squared, 2t, and e to the t plus 2. And I also tell you what are sometimes called boundary conditions. That the vector and the velocity vector at 0 happens to be 0, 0, 1. And the position vector, r of t, also at 0, ends up being 1, 1, 1. And we are being asked to find r of t. This would be the equivalent of a Calc 2 question. Do you know the kind of question where they tell you f dashed of x equals, and you work backwards to find f of x? Or they might tell you f double dashed of x equals something, and you work backwards to eventually get f of x. So I'm going to start with my acceleration function. What would I need to do to the acceleration function to get the velocity function? Vector function. Right? Keep dropping the word vector, but imagine that I say vector all the times I drop it, right? What would you need to do to the acceleration vector to get the velocity vector?
You do the opposite derivative, which is antiderivative.
Right. So add 1 to the power, you get that. Add 1 to the power, you get that. E to the t gets you e to the t, and 2 gets you that. But when you do antiderivatives, don't you also add in an arbitrary plus c? Isn't that what you typically get when you do this? So I'm going to call this plus c1, comma, plus c2, comma, plus c3. And I'm pretty sure I asked this question before, but it's worth asking again. See if you caught the answer the last time we did it. Why are those arbitrary constants not just called plus c and plus c? Why are they different?
Because any number could theoretically, when changed to derivative, become 0.
Right. So couldn't this one be 1, this could be 2, and this could be 99, right? So we need to distinguish. Now, I'm going to bring into play this boundary condition. What that says is that the velocity vector at 0 is this vector. Now, I know what the velocity vector at 0 should be. Shouldn't it be 0 cubed plus c1, 0 squared plus c2, and e to the 0 plus 2 lots of 0, so that's 1 plus c3. Are you comfortable with where that came from? And this has to equal 0, 0, 1. Now, if you do a quick matchup, doesn't that make c1 has to be 0, c2 has to be 0, and what does c3 have to be for this to match? What number does c3 have to equal for 1 plus c3 to match the z component, which was 1?
0.
0. So in this particular case, all of those guys are 0. So I can now write down the exact explicit version. It's t cubed plus 0, t squared plus 0, and e to the t plus 2t plus 0. Now, there's no reason in the world why they should all be 0. They just happen to be in this one question, right? Couldn't one of them been a 1 and the other been a 2 and the third one been a 0, right? Just happens to come out nice because I wanted them to come out nice. Now, if I take this guy and I integrate it, won't I get our position function, right? Our position vector. And this time it's add 1 to the power, divide by the new power. I'll just call them C1 again. 1/3 t cubed C2 and e to the t plus t squared plus C3. And this is where this guy comes in. So the position at 0 is given by this position vector. Nothing plus C1, nothing plus C2, 1 plus nothing plus C3. And this is going to be 1, 1, 1. Now, if I match these up, C1 is 1. C2 is also 1. But isn't C3 C3, sorry, isn't C3 0? And now I can say the position function, position vector. It's going to be 1/4 t to the 4 plus 1, 1/3 t cubed plus 1, and e to the t plus t squared plus nothing. Now, what that is telling me is all I need to know is what the acceleration, right, the change in velocity of a moving object is at any given value of time t, and tell me where it is. It doesn't need to be 0. Couldn't you do r of 1, r of 21, right? But tell me where it is somewhere at some point in time, and tell me what the velocity is at some point in time. And with those two, and only those two pieces of information, and the fact I know how the acceleration is changing through time, don't I now have where this object is at time? I think that's pretty interesting that you're able to get so much out of what essentially is just the acceleration of the object. Any questions about that, or are we good?
Good.
Good, right, let's move on. Just saying, covered, yep, did that, yep, did all that good stuff. Good. Okay. Imagine that we have our space curve, our roller coaster, and its position vector is a very nondescript function, right? And we are being asked, when is the speed at a maximum? So if this represented a roller coaster, right, where sometimes you go a lot faster and sometimes you almost stop, right, and then boom, you go fast again. It might be interesting, would you agree, to know when it's going at its maximum speed, right? Is it 3 seconds into the journey, whatever it might be? And probably, although they didn't ask it, but I think we'll calculate it anyway. Wouldn't it be nice to know what that speed was? So what's the fastest you're going to go on a roller coaster? Because if you're building a roller coaster on some kind of computer, right, designing it, once it's designed with all the corkscrews and all the things you've got, you don't want to spend $1 million building it and then finding out it goes too fast and it's too dangerous to use, or it's not that exciting because the fastest you go is 10 miles an hour, right? You know, you want to know a little bit about what the movement should be. Now, it's all essentially contained in the laws of motion, right? So if you know what the object looks like, right? If you've got a pathway for it, you should be able to come up with it. So first thing I'm going to do is I'm going to get the velocity. And I'm glad to say it's something very easy, so I shouldn't screw it up too much. And we get that. 2t, 7, 2t, take away 16. Look good? Now I'm interested in the maximum speed, so let's calculate the speed. It's the magnitude of the velocity vector. So it's going to be the square root of that guy squared plus 7 squared plus 2t take away 16 squared. And I'm going to do a little trick in a minute, but right now I'm just basically, plodding along, doing all the things you need to do. That's going to be 4t squared. That's going to be take away 3064 T's plus I think it's 256. I hope it is at least. So I'm going to get 8 T squareds. I'm going to get take away 64 T, add 305, I think it is. Does that look good? You know, if you something's not right, this is the time to tell me. Does that look about right? I'm happy with that one. I'm happy with that one. 4T squared, 32 doubled, and I believe 16 squared is 256. Right, we'll see it's right. So here's a problem. That ugly square root is going to be the speed of the object at any given time t. We want to know when it's going its maximum speed. Any suggestions about how you would do it? I don't need the details of what the answer is, but just how you would go about finding the biggest value for that function.
Taking the limit.
What, like the limit is t tends to infinity?
Yeah.
That would tell you the leveling off speed, you know, what it kind of does, but it might level off at 10 mile an hour, but before it gets there, couldn't it do a 50 mile an hour before that happens? So I was just thinking if that would work. My gut feeling it isn't, but I like your thinking. It's a good thinking. How do you find max and mins of things in calculus?
Derivative, right?
Yeah. So if I differentiated the speed function, wouldn't I be able to tell when the speed is at its biggest? I'm going to do a trick. I am not going to differentiate that because it's really ugly. I am going to differentiate what's inside. So here's my argument for why finding out the biggest value of this is the same thing as finding the biggest value of this. Would you agree that if this is a really big, and it has to be positive, right? Because you can't fit negatives inside square roots. If this is biggest, won't the square root of it be the biggest answer for the whole thing? And it's just less work. So I'll differentiate it. And I got 16t take away 64. So where do we go now?
And define where it equals 0.
Okay. And answer actually comes out real easy, isn't it? 4 seconds. And so this question said, when is the speed at its maximum? Its speed is maximum when t equals 4, right? They don't ask this, but I want to find out. What is this speed? Well, it's going to be equal to the square root of 8 times 4 squared, take away 64 times 4, plus 305. And I'm not going to do that in my head, so I'll just do it in the calculator. The square root of 8 times 16, take away 64 times 4, plus 305, and my calculator is not cooperating. Square root of 8 times 4 squared, take away 64 times 4, add 305, and anybody want to be in a roller coaster that's maximum speed is 13.3 miles per hour? Okay, wouldn't that be for the little tiny tots, right? And it's a train, right? And even then they cry because they're frightened, right? If I changed my units, if I went and said it was 13.3 meters per second, it's a little bit better, right? And if I said it was 13.3 kilometers per second, you'd probably be dead, because I think that G-force would just, your brain would hit the inside of your skull and kill you, right? So you don't want to be going at that kind of speed. But essentially, can't we find the speed at any given point? And if I can find the speed, can't we find when it's going at its maximum and when it's going at its minimum? Since it's speed, if the lowest number I can think of for a speed is 0, because speed is a scalar and it has to be positive, right? So you could be looking at a moving object, and really what you're doing is finding out when it's stationary. So can you imagine, you know, sometimes you go up to the top of a roller coaster and theoretically it hangs there for a second. At that point, isn't your speed 0 before you go down the other side? So you'd be finding, I guess, the tops and bottoms of a loop-the-loop kind of curve. How are we doing, guys? We hanging in here? This isn't too bad.
Pretty good.
Pretty good. Okay. So now we're going to look at what are called the tangential and normal components of acceleration. Now, this is not intuitive, at least in my brain. We know what the acceleration vector is. I mean, if I do it as its basic, isn't it just the second derivative of the velocity, the position function, right? That's acceleration. We have already calculated two guys. Can you remember the unit tangent vector and the unit normal vector? Remember those two guys? First derivative divided by magnitude of first derivative. The derivative of this guy divided by the magnitude of this guy. Right, really horrible guys to calculate, but we know, we've seen them. What you might not know, and this is a bit that to me is not intuitive, is that the acceleration vector is a linear combination of these two. And it doesn't matter what the curve looks like. You can spin it in its head and go back down the hole you just made. You can curve it any way you like. This guy is made up of two numbers. And these two numbers are called a little t, a little n. And a little t is called the tangential component of acceleration. And an has a very similar name. It's called the normal component of acceleration. It's something I'm not too aware of because I'm not interested in it, but evidently the fact that you can describe the acceleration in terms of these two vectors, and by the way, these two vectors are orthogonal to each other, means that if you've got a moving object, you can actually change the axes instead of using X, Y, and Z, which might generate really ugly equations that are hard to integrate and hard to differentiate and, you know, difficult to analyze. You can change them, it's called a change in basis vectors, to three other vectors. And those vectors are the unit tangent, that's like your X, your unit normal, and the one that isn't mentioned here is called the unit binormal, but the unit binormal is just a cross product of these two guys. And those three vectors, very often you can take the motion vector, right, the position vector, and convert them into these two guys, and you get much nicer looking math. Gives you some insight. So how do you calculate these two fellas? Well, I'm looking over here, make sure I've got all the bits and pieces. The tangential component is the dot product of the first and second derivative divided by the magnitude of the first derivative. And the other guy, the normal component, he is the magnitude of the cross product of the same two guys. Also divided by the magnitude of the first derivative. And I know it's magic. I just told you that's how you get them, but that's what they are. So all I need really is tell me who R of t is, and can't I just go through the processes and calculate that? So I'm going to pick R of t to be 2 times the cosine of 3t, 2 times sine of 3t, and 2t. I'll make it 3t. I like 3. That'll be nicer. So I find the derivative. Right, if you do this guy, you're going to get -6, the sine of 3t. Eventually, it's a chain rule. If you do this guy, you're going to get +6, the cosine of 3t. And if you do that guy, you just get 3. If I find the second derivative, you just differentiate that guy, and you get -18, the cosine of 3t. If you differentiate this guy, you get -18, the sine of 3t. If you differentiate that guy, you get 0. Oh, and I need to know that guy, and that guy, right? Once I know all these pieces, can I just plug them together? And, oh, these are all scalars. When you're finished, this guy is 42 or t squared plus 1, right? And this guy's -90 or 2t, right? There are no vectors in these answers. These are scalars. These are numbers, right? If you put t in, you'll get a number every time. So where shall I go? Let's do the first derivative time dot product with the second derivative. So if you take this guy and do a dot product with that guy, let's see what you get. This guy times that guy. You are going to get 6 times 18. So you're going to get 108 sine t 3t, cosine of 3t. And if you multiply this together, you're going to get -108 sine 3t, cosine 3t. And if you do this guy, oh, I didn't expect that, you're going to get 0. In fact, if you combine all of those, don't you get the answer? 0. That's going to make life easy. So I'll just write this guy down here until I need him. The fact that this is equal to 0, what does that tell me about these two vectors? The first and the second derivative, what does it tell me? Essentially, velocity and acceleration. What does it tell me? If that's velocity, say again?
90 degrees.
Yeah. Yeah, I'm not sure what they are, but you know, that's 90 degrees, isn't it? Any rotation you like, as long as you keep 90 degrees going. And I guess I should be continuing with the, what else do I need? Oh, I need a cross product and I need the magnitude of this guy. So let's put the magnitude of this guy in. So it's going to be the square root of this guy squared plus this guy squared plus this guy. And those two get me 36, and 36 add 9 gets me 45. So I got that guy. She's going to go here and here. So I guess I'll need a new piece of paper for the next one because the cross product might take a
Shouldn't
little
it
bit more.
be square root of 45?
Thank you. Yeah. And I need to know the cross product of the first and second derivative, and then I'll do its magnitude. So we're going to have an I, we're going to have a J, we're not going to have a K. And the first derivative is -6, the sine of 3t, +6, the cosine of 3t, and 3. And the second derivative is going to be -18, cosine of 3t, -18, sine of 3t, and a 0. So it's going to be so many i's, take away so many j's, plus so many k's. If I cover that up, I get nothing, take away 54, sine of 3t. If I cover the middle one up, I get nothing, take away 54 cosines of 3t. And if I cover this guy up, I get those two, which is 6 times 18. 108 sine squared 3t. Right, that's 2 positive. Take away a negative means add. Also 108 cosine squared 3t. So I get that vector. Oops. 2 negatives get me a plus, that vector. And do you notice that those two things combine to give you a nice answer? 108 sine squared plus 108 cos squareds. Don't they just get you 108? Does it matter that it's sine squared 3t or sine squared 2t or just sine squared t? No, same property holds in all cases. Now that's just a cross product. Now I'm going to get the magnitude of that guy. So it's going to be the square root of -54, the sine of 3t squared, plus 54, the cosine of 3t, all squared, plus 108 squared. Okay. If you take 54 and you square it, you get 2916 sine squareds. If you do this one, you get 2916 cos squareds. And if you do 108 and you square it, you get 11664. But don't those two combine to give you 2916? Add it to that guy. Let's see what we get. Add 2916, and you get the ridiculously ugly answer of 14580. Well, I think we've got all the pieces. We should be able to put them together now and get our two answers. So, the tangential component of acceleration is the dot product, which was 0, divided by the magnitude of the vector, which was the square root of 45. So that guy is 0. And
Hey, can you
the norm
that down right on the last? I'm sorry, the last piece of paper.
that one or
Yes.
that one? That one.
Yeah, that one.
Okay.
Thank you.
Now the normal component is the cross product. Then you take the magnitude and divide it by that guy. So that guy is the square root of 45. And this fella is the square root of 14580. And unless I was really lucky, but I guess I'll check it out, and that might not turn into anything useful. And would you believe it? It turned into something nice. Let me try something else. Oh, would you believe it? It's actually 18. So we have the tangential component is 0 and the normal component is 18. And that's all they want you to do. But I can now tell you that the acceleration vector is made up of 0 times the tangential plus 18 times the normal. So basically, isn't the acceleration vector traveling in the exact same direction as the normal? It's just doing it 18 times bigger. I have no idea what that means in an object that's moving. But if the normal vector is the one that tells you, you know, when you go around curves, the one that kind of pushes you into the side, this is telling me that the acceleration is towards the center. And it is a lot larger than the normal one, right? It's 18 units because, you know, that's 1 unit in length. So this would be 18 times 1. So it's 18 times as fast towards the center of a turning object. I could do that. Can you imagine something spiraling into the center? And since my original function was a helix, it might be a diminishing helix, right? You know, a helix that gets tighter as it moves. Interesting, if you're into that thing. Are we good? Because that's the last of that questions in that section. Last chance, you want to ask me anything about that section? We are done with chapter 13. It's a very short chapter, only 4 sections. Now we're on to our last chapter. We're going to look at multivariate functions, sometimes called functions of several variables. But we're not talking about 3D functions, right? Like space curves. We're actually talking about things that look like this. All the points in 3D space that look like that. So can you imagine finding an X, a Y, and a Z component that when you square the 3 of them and add them, the answer is 9. And you found every point where that was true. Have you any idea what that shape looks like?
Like a giant sphere, I believe,
It is. Do you know what the radius of that sphere would be?
around 3.
And do you know where the center would be? Where would the
At the
center?
origin.
At the origin. So I'm not very good at drawing things, as you kind of know, but kind of, yeah, made it 3D now, but give me a little shadow, right? A ball, sometimes called a sphere, sometimes called a ball in 3D space. It's no longer a line or a bent wire, right? That's what R of T does, right? It gives you a space curve, right? An object traveling through space. This here is surfaces, right? So surfaces are quite different. You've seen guys that look like this. Don't we call them a plane. Right, 3x plus 2y plus 4z. If you find all the points, don't you get a flat piece of paper at an angle? Can you imagine the z-axis is going this way and the x-axis is here and the y-axis here, right? The flat piece of paper. That is an example of a multivariate function, right? You can get a function that might be written like this. That's not as obvious what that is. Anybody want to have a guess? Because it probably should just be a guess, because it's not obvious what the surface that has that equation looks like.
I say a triangle.
I can kind of see why you would think that. Any other ideas?
Like a cylinder.
Oh, because this equals 1, yeah. Good guesses.
A
Not the right
circle?
answer, but good guesses. Yeah. It's called a paraboloid, and there's no reason you should actually be able to judge that, because you haven't seen enough 3D in your life to know what it looks like. But a paraboloid, the minute you stick OID at the end, it's talking about a 3D surface, right? So you have a paraboloid, a hyperboloid, can't think of any others, but there'll be an oid at the end of the name of the thing. It looks a bit like an acorn. Can you imagine a cup that goes up forever? Now, if you just stick a square root on it, so that's a paraboloid. If you stick a square root on it, it makes a huge difference to the shape. And I won't let you stress too long on this one. I'll take one guess and then we'll tell you what it is, because again, it's not obvious what it would be. Okay, any guesses before I do it? This is what you get. You get a cone. And when I talk about that, I'm only talking about the curved surface of the cone, right? I'm not talking about points inside it. I'm not talking about the points on that rim, although that is true. That's part of the answer. The only reason I'm doing these things is that it's hard to draw something infinite. So what you kind of do is you cut it off at 5 feet off the ground to get out at least the gist of what the shape looks like. So let me show you on some software what these guys are like, because it's very, very difficult, including my brain, although I kind of see things in 3D quite well. I'm still not great at it. That's what y, or in this case, I should say, z equals x squared looks like. If you orientate it a certain way, can't you see the parabola? But it's not a parabola, right? It's not a single line drawn in 3D space, right? It's not a spacegram. Isn't it an entire set of what we call a plane, right? A plane is like paper that's been curved, right? Now, if I add the y square to it, that's not the square, the y, come on. There we go. What can I tell you? There, can you see the paraboloid that I was talking about? Right? Orientation is everything, right? If you cannot, I don't know, that's probably the best orientation, right? I'm above, kind of looking down at an angle. You see that kind of, it looks like the bottom of an acorn to me, right? But an acorn that could keep going forever. Now, if you take this function, and that's this guy here, and you do square root, and you stick it round some brackets, and you click off on this darn thing. Okay, I think I've put something in here that needs to be put in the right place. Okay, I may just choose to do this from scratch because copying and pasting is not being my friend right now. Right, so here's my square root. And I'm going to put inside my square root a little bracket to make sure that it does it right. I'm going to do x squared plus y squared. Now, if I kind of take this one off, can you see the cone? Is it? You see how linear it is on the sides? How curved this one is? And how linear that guy is. Now, this time I should be able to copy and paste if the thing's going to let me do it. And I'm now going to put in only one change. I'm going to stick a minus in front. What's it going to look like with a minus in front of it? Let's get the other guys out of the way. When it's a plus, you get a cone that way. What's a negative going to do?
Will it just invert it?
It will. There you go. Well, once I click out, there you go. You see it? So we are dealing with multivariate functions. That means functions of more than one variable, right? And we're typically talking 2, 3, 4 variables, right? And for these shapes, as long as there's only an X, Y, and a Z, we should be able to visualize it. You can't really visualize 5-dimensional surfaces or even 4-dimensional surfaces, right? So we're not going to have software for that. We're just going to rely on the math to tell us what's going on, right? But in at least these situations, we can do relatively nice calculations. And that kind of cool that GeoBra allows you to play about with things. So if you're not sure what some looks like, can you just go there and type it in? Now, there are some awkward parts that you have to deal with. If I wanted to do, say, this plane here, right? If I went to, I'm not going to zoom back and forward, but I'm typing in 3x plus 2y plus 4z equals 10. You're just going to trust that that's what I'm doing, right? GeoBra is totally okay with that. You would see an equation of the plane. Now, if I try, because I think the next one's not going to work. If I try x squared, and maybe it will prove me wrong, which was nice, y squared plus z squared equals 9. Oh, GeoBra is nicer than I thought. I thought it wasn't going to handle it, but it was. If it didn't handle it, don't you just have to rearrange this to say z equals? If you had to, right? Any questions so far about multivariate functions and what they look like and what they are? They're just surfaces, right? Infinite surfaces typically, but in some cases like this, it's an enclosed sphere.
I was just wondering, is GeoBra something we can use on like a quiz or exam?
Yeah, why not? It's just like using Desmos.
Okay, thanks.
But I think you've got, if I'll check, but I think I've gave you some questions. Yes, I did. Where here is the function, tell me which one of these 5 pictures is it, right? So I'm actually encouraging you to do it. So far, so good? Skimming through these. Yeah, there's, I'm telling you the number right now. When you're doing question 4, you go to GeoBra, you've put in the equation, and then there's 5 guys to pitch. So it's like the first one matches picture 5, the second one is picture 2, the third one is picture 3, and so on, right? So there is a question where you do exactly that. Let's talk a little bit about what are called contour maps. If any of you have done military service, especially I would assume on land, military service, so Marines, infantry, whatever, artillery, whatever, those kind of things, you probably had to deal with ordnance, we call them in Britain anyway, ordnance survey maps, OS maps, right? Does anybody know what the heck I'm talking about?
Yeah, you can use them to navigate. A
Exactly.
lot.
You're saying that it's something that you use more than satellites because satellites don't always available.
Oh, yeah, yeah.
Right. So what essentially a contour map is, it's a region, you use flat 2D paper, but you're using it to try and describe a 3D surface. Because essentially, can you think of the surface as being the hill in 3 dimensions, right? So if I gave you a contour map and it was made up of, say, these circles, and I'm trying my darndest to make them right, but you know, you got to forgive me if they look a little bit weird. We should be able to, if I tell you that this guy is a height of 5, this guy is a height of 4, this guy's a height of 3, this guy's a height of 2, and maybe a dot, a height of 1. You should be able to take that guy and recognize what the surface would look like. Okay, so I'm putting you in the spot. If you had to go there, are you climbing a hill or are you walking into a funny looking valley? Which is it?
If you're going from 5 to 4, you're going downhill. If you're going from 1 to 5, you're going uphill.
Okay, so if you wanted to derive this shape, I don't know how good I'm at 3Ding, but do you get the idea that that would be a cone going down the way, right? The biggest circle is 5, 4, 3. Now, if I take that exact same picture, I don't want to redraw it because I'm lazy, and I do 5, 4, 3, 2, and 1, right? Same picture, but I tell you the heights are now 1, 2, 3, 4, 5. Aren't you looking at a very similar shape? But the cone's pointing that way, right? So you would be walking up a very weird looking hill, right? Now, if you're into orienteering, I don't know if that's a sport anymore, where you get a map and you've got like 8 places to get to, and you're not allowed to use phones or GPSs, you just got to use your own knowledge. Plus, don't you have to judge what would be the most comfortable route to get to the thing? Because straight lines aren't always a good idea, because going up that mountain to go down the other side, maybe it would be better if you just went round it, you know, that kind of thing. I'm taking that's probably military. Don't go up a hill and downhill because it's a straight line, you know, because people will see you and shoot at you as well, right? So you got ordnance survey. These allow us to visualize 3D surfaces. So here is a 3D contour map. And I'll make that a height of 3, a height of 2, and a height of 1. And maybe make the guy in the middle 0, a single point. What would that look like in 3D?
Like a upside down pyramid. Or
It
not
would.
a pyramid.
Yeah, pyramid's a good, I get the gist of what you're saying. This is not going to work because I'm useless at drawing, but it would kind of look like, you know, yeah, I'm useless. Do you know step pyramids that go up in blocks? I mean, if I change the numbers, it probably would work better. It would look like this, right? And then I think the Mayans, for instance, didn't they build a lot of their pyramids more like this?
Ziggurats or whatever they call
Yeah.
Yes, exactly. Right, so you can visualize a 3D shape by simply doing, being given its contour map. So what I'm going to do now is show you how you can create a contour map so that you can visualize what the surface would look like, right? So I'm going to pick, oh, what am I going to pick? Can I pick something easy? Yeah. Suppose I want to visualize what the contour map of x squared take away y squared is. Right. So I'm going to create a contour map, and then once I've got a contour map, I could then try and visualize the surface, but we're only going to do the contour map. So this is what you do. You choose essentially heights. So I want you to think of f of x, y as being equivalent to the height. So I'm going to choose a height of 0, a height of 1, a height of 2, and a height of 3, and then so on, right? So what we're essentially doing is doing horizontal slices through some kind of weird hill, right? Well, weird hill or valley, right? And for each one of them, you go back here and you say, okay, x squared minus y squared is 0. X squared minus y squared is 1. X squared minus y squared is 2. And x squared minus y squared is 3, and so on forever. And you probably want to go into Desmos and sketch each one of these, because aren't they in 2D? Aren't these just curves? You trust me? These are all curves. And if you pick the first one, right? If I rearrange that one, it's the same as that. And that makes x equal to plus or minus y. So that one is a straight line going that way, and it's a straight line going that way. And that's what you get when the height is 0. Now, if you do a height of 1, right, this guy here, you get what's called a hyperbola, and it kind of looks like this. Can you imagine I just put it into Desmos, and that guy is him, right? So that's a height of 1. And then you do a height of 2, and you get a guy that looks like this, and a guy that looks like this. And run shorty colors, and then you do a height of 3, and you do a height of 3, and it looks like that. So you can see you can basically take slices. Now, if you're looking at this from above, do you see how it's high going this direction? Aren't you going downhill? Oh, and by the way, no, that's the right way. Yes, it could have been this way, but I think you'd have to switch the X's and Y's around, right? So I'm pretty sure it's that way. Right, if I was looking at that shape, do you see a kind of hill, very badly drawn, that kind of comes down this way and goes up that way? Side view. Can you see the hill I'm talking about? High, lower, 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 right? Right. High, lower, lower, lower. I don't know how convincing that is, but that is how you would do a level curve. And I think I should do Desmos for the next one, because my pictures are not as good by any stretch of the imagination as good as Desmos. Okay, what happened there? Some of my lights just went on me, but we can keep going. Right. So let's, oh, first I'm getting Desmos, that's right. Okay, I'm ready. And what function shall I do it with? Let's pick one of theirs, that way it's more realistic. Where are you? Come on. Okay, this one will do. This happens to be question 7. And the surface is that guy equals the square of x plus y. That is the equivalent to saying z equals the square of x plus y. Okay, so we are going to do a contour map of this relationship and see what they look like. So I'll nip over to Desmos. Desmos is hiding. Where are you, Desmos? I've lost it. There, I found you again. Okay. I may have to go back out and then to find it. There we go. Right, you're looking at Desmos now? Right, now the function I had got was the z equals the square root of x plus y. So I'm just going to go and do square root of x. And well, I don't need to put those brackets, do I? Square of x, get out the square root and add y and make it equal 0. And there's my first. Right. Everything on that curve has a height of 0. Now I'll copy, I'll put that one down and I'll make this a height of 1. And then I'll copy this one and I'll make it a height of 2. And then I'll copy this one and I'll make it the height of 3. Can you see the contour map? Right? And then there'll be what, 4 pictures and one of them will look like that guy, right? And that's the one. This one looks like it's coming up and going down the way. It's not a very interesting curve, actually. Let's see if I can pick something more interesting. It's one of these guys. Looks like it's going to be that one. Right, let's find something towards the bottom. Oh, that looks interesting. Okay, there's a good one. I'll pick that one. So get rid of all these guys. And this time we're going to do a contour map. And it's y divided by, and on the bottom I've got x squared plus y squared. And hopefully if I put equals 0, which is basically the x-axis, and then if I put equals 1, oh, you get a circle. And if I put equals 2, you get a different circle. And if I do equals 3, you get a different circle. Let's zoom in on that. Can you imagine that that shape is essentially climbing upwards towards the origin, right? It's basically lots of circles. You can imagine the Egyptians decided that they liked circles instead of squares or rectangles, right? And so they build their ziggurat with a big circle. And instead of putting their next one right in the middle, for some reason they build it always on the south-facing side because that's what they wanted to do. Can you imagine the next circle would be here and the next one would be here? So what I'm seeing is circle upon circle upon circle. Can you imagine what that shape might look like if you smoothed it off? And the one that looks like that, does it have 2 values? Oh, I know what they did. They also put negative values down, which might seem strange, but actually negative values do make sense. What would a height of -3 mean?
It's a depression.
Right, it's below, essentially below sea level, right? It doesn't happen much, but I believe isn't there parts of Israel and the Dead Sea that are actually lower than sea level, and there's a sea there, right? Because you could be 50 feet below sea level. Not a very safe place to be because You know, if it rains, isn't that the first place it fills up? But technically you could get it. So if I move this shape back a bit, can you now see it looks like concentric eights, which happens to be, if I move this over, I don't know if you can see it. Can you see the answer to question 10? Are you still looking at GeoBra, or can you see question 10 now?
See question 10.
Okay, do you see the one that's highlighted as concentric eights going that way? So if you want to find a contour map of a surface, couldn't you do this? And then when you look at the shape, you can try and imagine what that looks like. My brain is telling me that this is coming up from both sides in a very circular way. Really weird, quite interesting shape. Actually, that is the shape, isn't it? Yeah. Okay, I've got enough. I'm going, right, for the last thing, while I'm doing this, why don't you lot do your attendance, your last name? I want to do GeoBra. I want to see what that weird shape looks like because it's got my interest now.
I think that it is the inverse of the previous function that you have.
You think? I'm not saying you're wrong. I'm just.
The denominator should be 1.
Right, I hope I've got the same question as we had a minute ago. If not, this one will do. Right, are you looking at GeoBra now? Right, if we zoom in on this shape, can you see on this side, these are the concentric circles? Right, there, does it help if you see it that way? Right, and it looks like something really interesting has happened because although I didn't pay attention to it, do you see the bottom half? Instead of growing bigger, they get smaller. And the other side gets bigger. So it's going up on one side and down on the other. What a really cool shape. So if this was representing two bodies in 3D space, right? So if you imagine this was a space-time curve, an object that's traveling along here, if it hit that thing, wouldn't it basically get repelled from the center? You wouldn't be able to get to the center. But what happens if you get round the corner of that? Won't you get caught by this guy and basically I have a black hole? So that would be a weird, there'd be a planet or a sun that had anti-gravity that was trying to stop you from getting closer to it. The gravity well, it would be a gravity well, it'd be a gravity hill. And right next door to it, equally dangerous, isn't, you know, that keeps on going, isn't a gravity well, which basically is drawing you into that shape. So I have just invented the Robertson black hole. So I'm making a prediction that somewhere in the universe, because the universe is massive and almost everything happens in the universe somewhere, there is a very strange part of the universe that has a black hole and a white hole right next to it. And one of them is sucking things in and the other one is pushing things away. I'm famous. I've just invented something that doesn't exist.
I thought it does.
Well,
Like a
now
true
that I've said it,
mathematician.
it exists, right? But I don't think anyone has found one of them. Right, well, that's it. We've had a good day today. I only have one more day to see you. And I want to scare you because it's scaring the heck out of me. We have Thursday, we have week 10, that's 3 days, and we have a revision day Monday. Are you suitably scared? We are almost, it's almost upon us. So try, try and get time, guys. Try and figure out a way of getting another couple of hours here or there so that you're prepared for the final. 30% of your grade is not to be scoffed at. I have sent out the report. Hopefully it's pretty accurate now. There was a little hiccup on the first one, but I've cured that. I'll give you an idea of where you are and what you need. Okay. Have a nice day. I will see you tomorrow. Bye-bye.
Have a good.
Thank you.
You're welcome.
So I had something about my grade. That's good.
Sure.
All right, thank you.
Thank you, Professor.
You're welcome, Thomas. I'm going to get that thing. I'm trying to write down. I'm trying to find a piece of paper where I wrote it down,
All right.
which is to do with the fact that I haven't given you the points, or not everyone the points. Where's that thing? Come on. Nope, nothing.
Well, it's section 11.11.
And I now have it. Now that you
Alright.
said it, 11:11, fix the
Mhm.
function. Right, what isn't working for you?
So the other thing that I think is wrong is week
Uh-huh.
6. It says I have a participation grade score of 2 out of 3.
So you've never missed a day, you essentially tell me, right?
Yeah. I don't.
Okay, I can't recollect you ever missing a day, so let me
Yeah, I don't. Either.
pick that one up. Thomas C. Week 6.
Mhm.
Week 6 is 2 out of 2. There are only 2. Oh, did I say it was 2 out of 3?
Yeah,
It's 2 out of 2. I just said 3.
that makes sense.
Right, because that was the day that we got our midterm. That was Monday.
Yeah.
Day off Tuesday, and I only saw you Thursday. So you get 1 for homework on time and 1 for attending. So there's
That
2.
that makes sense.
Right. So that's what that one was. Right. So it's 2 out of 2, not 2 out of 3.
All right.
But now I've got that, I might as well change it right now. So for the future, we don't have that issue when people are, the last check. So glad you
Questioning
found
about that.
Yeah. It's easy fix, but it's also easy to miss.
Okay.
So week 6 is now, I won't bother printing that because it's not a biggie. And now I've fixed it for everybody. Yeah. I'm pretty sure the total is correct.
Mhm.
You want to check that just in case I graded it as 3 and not 2.
So are you sending out the new email?
No. So
All right.
just check the percentage that you would have got and see if it matches your participation grade.
So I have 2 out of 3, and you said there's only 2
It's really
points
2
to
out
commit.
of 2. So I've now changed it to say 2 out of 2. The number at the end isn't the thing that gets added anyway. The number at the end is just how many points it's out of.
All right.
So that shouldn't have affected the total, because the total is what you get when you add them up.
Here, let me.
The numbers that you've got.
Yeah, I'm doing a quick check.
Right.
Times 7 plus 2.
Get my spreadsheet opened up for you. Right, I have a total of 26. So 4, 4, 4, 4, and 4. That takes me 20.
And you said I have a
No,
total of
3,
I got
6, 9, 12, 15, 16, 17, 18, 19, 20, 22, 23. So it should be out. Well, okay, let me check that total again. I think my total is not right. I've got 26, but if forgetting that it's 3, you can get 4 because you did your homework, but it's only counted as a 3 for the total on the bottom.
Mhm.
So 3, 6, 9, 12, 15, 16, 17, 19, 22, 23. Should be out of 23 and
think
not
it's-
26.
I think it's supposed to be 30 out of 24. Because if you take there's 8 weeks here.
Right.
Yeah.
But we had week 6 had, oh, wait a minute, you do get 1.
So it'd be 4 times 7, which would be 28, plus 2 for the odd week of week 6. That'd make 30. And if you do 3 times 8, that would make 24. So it'd be 30 out of 24.
Okay, I'll put the 24 in. See what that
Oh,
does.
wait. It'd be 30 out of 23 because of the odd week again
Okay,
of week 6.
which I think is what I changed it to. Let's double check. Okay, that's done.
And it says I get a overall grade of 130% on that
Uh,
section.
And let's check C. You are correct. That's what the new spreadsheet says. So
Alright.
you basically, you're getting 3 percentage participation points for doing your homework on time,
All right.
which makes sense. Right, fixed.
All right.
Okay,
Okay.
bye-bye for now.
Okay. See you later. Bye bye.
See you later.